Class 12th Chemistry, Haloalkanes and Haloarenes, and in this video we will discuss about stereochemical aspects of nucleophilic substitution reactions. Dear student, stereochemistry is a separate branch of chemistry and it deals with many concepts. Okay, but in this video we will limit our concepts only to nucleophilic substitution reaction. First of all, we will discuss some terms. First one is plane polarized light. Light whose electric field oscillates in just one plane is known as plane polarized light. It is obtained by passing ordinary light through Nicol prism. This is one special type of prism which is made from the special materials. Okay. This is the ordinary light. Its oscillations are in all the planes, all the sides. When this light is passed through the Nicol prism, its oscillations are restricted to only one plane. This type of light is known as plane polarized light. Okay. Optically active compounds. Compounds which rotate the plane of plane polarized light are called optically active compounds. The angle by which the plane polarized light is rotated is measured by an instrument called polarimeter. This is the schematic diagram of polarimeter. This is ordinary light, okay, and this is the path of propagation. When this light is passed through Nicol prism, its oscillations are restricted in the one plane, and now we will get the plane polarized light. And when this light is passed through the sample, then this direction of this plane polarized light is rotated. It may be clockwise or it may be anti-clockwise. The angle of rotation is detected by this detector. Okay. If the compound rotates the plane polarized light to the right hand side, that is to right, that is clockwise direction, it is called dextro-rotatory, Greek for right rotating, and this is also known as D form and is indicated by placing a positive sign before the degree of rotation. If the light is rotated towards left, that is anti-clockwise direction, the compound is said to be levo-rotatory or L, small l, okay, form, and negative sign is placed before the degree of rotation. Such, that is dextro-rotatory or plus, and levo-rotatory, that is minus, isomers of compounds are called optical isomers, and the phenomena is termed as optical isomerism. Asymmetric carbon atom or chiral carbon. A carbon atom that is attached to 4 different types of atoms or groups of atoms is known as asymmetric carbon. You can see this diagram. This carbon has 4 different atoms like this H, F, Br, OH, all are different. That's why this carbon is known as asymmetric carbon or chiral carbon. This is also known as stereo center. The molecule that contains asymmetric carbon atom would lack symmetry and is referred to as asymmetric molecule. The mirror image of the molecule is not superimposed, that is overlaid on the molecule. Again, you can see this diagram. This is asymmetric molecule containing asymmetric carbon atom, and this is the mirror image of this. This is not superimposed, that is, we can say both are not superimposed to each other, not overlapped to each other. Simply you can say, if we pick up this molecule and put on this, then you will observe that the arrangement of the atoms will not coincide. This is called not superimposed or non-superimposable mirror images. The asymmetry of the molecule along with non-superimposability of a mirror image is responsible for the optical activity in the organic compounds. Chirality. The objects which are non-superimposable on their mirror image, like a pair of hands, are said to be chiral, and this property is known as chirality. chiral molecules are optically active. The objects which are superimposable on their mirror images are called achiral, and these molecules are optically inactive. You can see this diagram. An object that cannot be superimposed on its mirror image is called chiral. Like this is our hands. These are they are related to each other as a non-superimposable mirror images. Like this is our feet. These are the chiral objects, non-superimposable mirror images. These are the some items in our daily life, like this the sphere. These are non-chiral objects, superimposable mirror images. Okay, a sphere, a cube, a cone are all identical to their mirror images and can be superimposed. Our left and right hands are non-superimposable on their mirror images. Aids that can assist us in recognize chiral molecule. How can we find out that given molecule is chiral or achiral? Okay, one such aid is the presence of a single asymmetric carbon atom. Now consider propane 2-ol. This is the structure of propane 2-ol. Okay, this is carbon, this is CH3, and this is CH, and on this carbon atom OH group is attached. If you number, this is 1, 2, 3. OH is attached on the second carbon atom. That's why this is propane 2-ol. And you can also represent this. Okay. And if we get the mirror image of this, we will get B. And when this B is rotated by 180 degree, we will get the C. Now see, propane 2-ol, that is compound A representing this one, does not contain an asymmetric carbon. Now why it does not contain asymmetric carbon? Because in this case these two groups are same. All four groups are not different. That's why it does not contain asymmetric carbon. As all the four groups attached to the tetrahedral carbon are not different. We rotate the mirror image B of the molecule by 180 degree, then we will get the structure C, and try to overlap the structure C with the structure A. These structures completely overlap. Now if you place this as such on this one, then you will observe that C is completely superimposed on this A. That's why we can say propane 2-ol is an achiral molecule. Another example, consider butane 2-ol. This is 1, 2, 3 and 4. Okay. Now this carbon attached with the 4 different atoms and group of atoms. This is CH3, this is H, this is OH, and this is ethyl, CH2, CH3. Now we gave its representation as a D, its mirror image is E, and after rotation 180 degree we will get F. Okay. Butane 2-ol has 4 different groups attached to tetrahedral carbon. That's why this is a chiral or chiral. Now just if you try to overlap or superimpose this to this one, you will observe that these are not overlapped. These are not superimposed. That's why these are related to as non-superimposable mirror images, and this butane 2-ol is optically active compound because this is chiral molecule. Okay. Enantiomers. The stereoisomers related to each other as non-superimposable mirror images are called enantiomers. You can see these are this is a one molecule and this is its mirror image. These are non-superimposable mirror images, and this pair is known as enantiomer. Some more example like 2-chlorobutane. Just write its structure. This is CH3, this is CH, this is Cl, this is CH2, CH3. Okay. Now this carbon, this is the stereo center, asymmetric carbon. 4 different atoms or groups are attached to this carbon. The same way, 2,3-dihydroxypropanol. 2,3 dihydroxypropanol. Now if you see this carbon, this is one group, this hydrogen is another group, this OH is third group, and this CH2OH is fourth group. All are different. This is bromo, chloro, iodo, methane. This carbon attached with the four different atoms Br, Cl, H and I. Okay, 2-bromo-propanoic acid. Again see this carbon. This is 1, this hydrogen 2, this is bromine 3 and COH 4. All are different. Okay. Enantiomers possess identical physical properties, namely melting point, boiling point, refractive index, etc. But in what way they differ to each other? They only differ with respect to the rotation of plane polarized light. If one of the enantiomer is dextrorotatory, the other will be levorotatory. Racemic mixture or racemic modification. A mixture containing two enantiomers in equal proportions will have zero optical rotation. Why? As the rotation due to one isomer, which is in right hand side if you assume, will be cancelled by the rotation due to other isomer, which will be in the left hand side. Okay. Such a mixture is known as racemic mixture or racemic modification. A racemic mixture is represented by prefixing DL or plus minus before the name. For example, this butane 2-ol, and this represents that this butane 2-ol, sample of this butane 2-ol contains equal proportion of dextro and levorotatory isomers. The process of conversion of an enantiomer into a racemic mixture is known as racemisation. See one example 10.8. Identify chiral molecules in each of the following pair of compounds. Like this, two compounds are given. Again, what is the identification of chiral molecule? Carbon, that is a carbon containing four different atoms or group of atoms attached to that one. Now this carbon. Okay, now again see this is CH3, Br, OH, all are different. Now in this CH3, this two B are same. That's why your answer is this one, first one. Now in this case, this is the carbon. Okay, now this is attached with OH, CH3, this H, and this group is considered as a one group. All four are different. But in this case, this is the carbon. You can say this one and this one is the same group. That's why your answer is this. This is a chiral molecule. Okay. Now among these two, between these two, now you can say this carbon. This is attached with, this is CH3, this hydrogen, and this is the one group. All four are different. While in this case, this carbon is attached with this one group and these two hydrogens, which are the same. That's why your answer is this one. I think you are able to find out, identify the chiral molecules in the given substances or given pairs. Retention. Retention of configuration is the preservation of spatial arrangement of bonds to an asymmetric center during a chemical reaction or transformation. Okay, if there is no change in the spatial arrangement of bonds, then that is called retention of configuration. In general, no bond to the stereo center is broken. The product will have the same general configuration of groups around the stereo center as that of reactant. Such a reaction is said to proceed with the retention of the configuration. Now just see, this is this molecule, this is a levorotatory. Okay, this minus symbol represents levorotatory 2-methyl butane 1-ol, and this is react with the HCl. Then this OH is replaced by Cl. We will get this one. This is dextrorotatory 1-chloro 2-methyl butane. Now this is a retention of configuration. How? Now you can say this is the stereo center. Okay, and this is stereo center. In this conversion, no bond is broken around the stereo center. This bond is broken, but this is not directly attached to the stereo center. That's why this is called retention of configuration. Okay. Now one more thing we have to remember. Optical rotation is not related with the retention of configuration or simply configuration. Optical rotation is different thing and configuration is different thing. That's why this is a levorotatory and this is the dextrorotatory. Okay. Optical rotation is different and configuration is different. Now if we compare this inversion, retention and racemization, this is our main molecule reactant. If this react with the nucleophile Y, okay, this X is replaced by Y, will get A. Now if the same molecule react with the Y, that is then X is replaced by Y and we will get this compound B. And if this is again treated with the Y, if we will get the mixture of A and B, then how can we say which is inversion, which is retention and which is racemization? If A is the only compound obtained, the process is called retention of configuration. Okay. Now you can say this is the conversion of this into this. This is called retention. If B is the only compound obtained, the process is called inversion of configuration. This one. If this will convert into this one, this is called inversion of configuration. Just you see the arrangement of a group of atoms around the stereo center. Okay, this and this. If you compare this one, this is inversion. If a 50-50 mixture of A and B is obtained, then the process is called racemization and the product is optically inactive like this. If we get both A and B, then this is racemic mixture and this is optically inactive. Now SN1 and SN2 mechanism with examples of optically active alkyl halides. SN2 reactions of optically active halides are accompanied by inversion of configuration. Now if alkyl halide undergoes reaction through SN2 and that alkyl halide is optically active, okay, then this will proceed with the inversion of configuration. You can say this. This is again levorotatory 2-bromo-octane and this is dextrorotatory octane 2-ol. But this is inversion of configuration. Just see the arrangement of atoms around the stereo center. In this case, this Br nucleophile is in right hand side. In this case, this OH nucleophile is in left hand side. Okay. SN1 reactions of optically active halides are accompanied by racemization. Okay. Now, if optically active halide undergo reaction through SN1, then this will result in the racemization. That is, we will obtain the racemic mixture. Now, you can see this one is proceed through the SN1 mechanism. This carbocation is formed. Okay, in the first step. And in the second step, this carbocation may be attacked by this side or from this side. That's why we can get either both, that is dextrorotatory butane 2-ol and levorotatory butane 2-ol. Now we can say actually this carbocation is symmetrical. This is planar molecule. That's why nucleophile can attack from either side and we will get the dextrorotatory as well as levorotatory compounds. That's why this result, that is SN1 reaction of optically active halides accompanied by racemization. Carbocation formed in the slow step being sp2 hybridized is planar, and that planar carbocation can be attacked from both the sides and we will get both optically active compound, that is dextrorotatory and levorotatory. Okay student, thank you.